So in the last class, we had started talking about you are given a filter that you are interested in approximating by an FIR filter. And how do you do that? We had gone up to the discussion of what we called window method or truncation of the filter impulse response. So just as a reminder, what happens in practical DSP systems is the first step you do involves you first obtain the desired frequency response HD of e to the j omega. You figure out what is the frequency response in the discrete time that you need, which is obtained through application specifications, conversion from the continuous time to the discrete time. And once you have that, then the next step you do is do an inverse Fourier transform to get the desired impulse response. So this is desired impulse response, but in pretty much all cases, this ends up being an infinite impulse response, so you can't implement it. So what we want is that somehow approximate this infinite impulse response by a finite duration impulse response that whose frequency response is as close to your desired frequency response as possible. So we want something we'll call HTN such that HTN is equal to 0 for all less than minus m and n greater than capital M. So the length of this filter is 2m plus 1. And this HTN has a frequency response which we call HT e to the j omega. And then where we ended last time was we want this, the third step is want HTN, HT e to the j omega to be close to HD e to the j omega. And the way we defined the closeness was through the mean squared error. And when we did all the calculations using the Parseval's identity, what we end up getting was that HTN should be equal to H of dn for n from minus 1 to minus m to m. Okay. This is the formulation that we had gotten. And this is, of course, a non-causal filter. So how do you obtain a causal filter from this? You just shift this filter by an amount m. So step 4 is shift HTN by m to obtain a causal filter. H of n. So H of n can be defined as HT of n minus m. Or more explicitly, it can be just defined as HD of n minus m for n equal to minus m to m and 0 otherwise. So this is the procedure for designing an FIR filter from an infinite impulse response filter. The procedure is simply from your desired frequency response, you get an impulse response, which is going to be infinite duration. Then you simply shift that impulse response by an amount capital M to the right. And then you truncate everything. You throw away everything other than from 0 to 2m. Okay. So this filter has length is still 2m plus 1, which is equal to n. Okay. And this kind of procedure, this is called window method for the following reason. This, if you look at this expression, you can obtain this expression in the following way too. Let's say that I define a window Wn equal to 1 for n from 0, 1 up to m up to 2m plus 1. Okay. These indices should be from 0 to m plus 2m plus 1. 0, 1 up to 2m. This should be up to 2m. So I can define this Wn, which is called a window, which basically just looks like all ones from 0 up to 2m. Okay. And I can say that Hn is nothing but Hd of n minus m multiplied by W of n. So this equation and this equation, this double star, they are both conveying the same meaning. You are multiplying a function with another function which is 0 for everything except from 0 to 2m. So this is equivalent to Hd of n minus m for n from 0 to 2m and 0 otherwise. So this procedure is called windowing because of this, that you are basically looking at your infinite duration impulse response, and then you put a window of size 2m plus 1 on top of it, and whatever is inside the window you keep, whatever is outside that window you throw away. Okay. So this kind of a window, as the shape shows, if you look at the shape, this looks like a rectangle. So this window, this is called FIR filter design. By rectangular window. So we'll look at concrete examples of this for high pass, low pass, band pass, and band stop filters. But all that this mathematics is saying is you get an infinite length filter, you first shift it by m to make it causal, and then you throw away everything except from 0 to 2m. Okay, we'll now look at some examples to see how to design FIR filters using the rectangular window method. And these examples are all for special classes of filters that we are interested in. So let's look at first an FIR low pass filter. So based upon the specifications, you obtain that what you really want is in the discrete time a low pass filter, and you say that the cutoff of that low pass filter has to be omega c. So ideally what you want is a filter that looks like from minus pi to pi, an ideal low pass filter with a cutoff of omega c. This is your desired frequency response. So if you write that down mathematically, hd of e to the j omega in this case is just 1 for absolute value of omega less than or equal to omega c, and 0 for omega between omega c and pi. Okay. So that's the first step that you need for designing a filter. You first get your desired frequency response. Now, based upon that, you take the inverse Fourier transform to get the impulse response. Now, we have seen that many times. By now, you should be an expert in writing down the impulse response of a low pass filter. That is sine of omega Cn over pi n. And n goes from minus infinity to infinity. So this is, as we know, an impulse response with infinite duration. And now the goal is we want to limit it to a finite duration. So how we do that, we first shift the response. So if we say that, say, n equal to 2m plus 1, we shift this hdn to get hd of n minus m, which simply is equal to sine of omega c of n minus m over pi of n minus capital M. This is still infinite duration. And the final step is that we now define h of n to be hdn minus m wn, which is the rectangular window. So that is equal to sine of omega c n minus capital M over pi n minus capital M, but now from n equal to 0 to 2m and 0 otherwise. So this is how you will obtain an FIR filter, and by doing this shifting, you basically guarantee that you get a symmetric filter. So in this case, you will, if you follow this setup, you will get a symmetric filter which will be of length n equal to 2m plus 1. So let's go back to the frequency design analysis tool in MATLAB, and hopefully now some of the terms in this tool will start making sense. We are designing a low pass filter and we are interested in an FIR filter. And now when we select the window method, this is exactly what it means, the window method that I just described. Now there can be many different types of windows. We'll come to those windows later, but right now we have only studied the case of a rectangular window. So when you select the window method, an option comes, what kind of window do you want? Because in reality, you can multiply your hd of n minus m with a window that is not necessarily a rectangular window. So I am interested in a rectangular window. I'm going to work with a filter design in the discrete domain. So I say 0.3, for example, and I specify the length of the filter through the order, which is length minus 1. So let's say I'm interested in a length 20 filter, or let's look at a smaller length, 10. This is what the frequency response looks like. We have seen that before, but I now want to look at the impulse response. And this impulse response, as you see, goes from 0 to 10. So my 2m is 10, and it is just part of the sink. So if it's not clear, let's increase the length of the filter to make it more obvious. Let's do a 50 length filter, and I'll just go back here and come back so that it shows me the full picture. Okay. And now you can see that all this is your ideal impulse response was going from minus infinity to infinity. What the rectangular window has done is simply shifted your first impulse response, that infinite impulse response, to by m, which is half the order. So 50 divided by 2, that's 25. And once it shifted it, it basically cut off everything other than from 0 to 50. So what you see is part of a sink. That's your FIR filter. Okay, as simple as that. Now we can do the same for high pass filter. We can say we are interested in designing an FIR high pass filter. Once again, the first thing you need is the cutoff of this high pass filter. You say that is omega equal to omega c. So you are interested in a high pass filter which looks like the following. It has a cutoff at omega c and minus omega c. And from that, you just write down the desired frequency response. So it is 0 for absolute value of omega less than omega c, and 1 for omega c less than or equal to absolute value of omega is less than or equal to pi. Okay. So once you do that, you take its inverse Fourier transform, you get HDN, which I'm just going to write down the formula 1 minus omega c over pi for n equal to 0, and minus sine omega cn over pi n for absolute value of omega greater than 0. So it looks like an inverted sink after n greater than 0, and it's of course an impulse response which is infinite duration. So what does the rectangular window method ask you to do? It says simply shift it by amount. So we shift HDN by amount capital N equal to, capital M equal to 2n equal to n minus 1 divided by 2. Okay. You shift it by this amount where n is the length of the filter. And then you keep only the things that are between 0 and n minus 1. So how do you get your real impulse response from Hn? Well, first of all, so for absolute value of n greater than 0, that simply comes out to be minus sine omega c of n minus m over pi n minus m. For n equal to 0, 1 up to n minus 1, except n equal to capital M. Okay. So this case you have to handle separately, right? Which is this case? You are replacing n by n minus m, so that is n minus m equal to 0, which implies n equal to capital M. So you have to handle the n equal to capital M case separately, and that is 1 minus omega c over pi for n equal to capital M. So again, whatever was your impulse response, effectively you just shifted it to the right by amount m, and you threw away everything except whatever is between 0 and n minus 1. Okay. So I want to now again show you the shape of that impulse response, which is the finite impulse response, by now designing a high pass filter. Everything stays the same. I'm going to just have a normalized cutoff frequency, let's say 0.6 pi, and I say design the filter. I'll change the view so that it comes back, and this is what it looks like. It is again, and it is a sink, right? But with the negative, the sink signs are shifted. Your typical sink has a positive value around here. Here it has a negative value. Right? But it looks very much like the formula that we derived earlier. The only thing is it goes from 0 to 50 rather than going from minus infinity to infinity. So, but the window method by rectangular window is as simple as just truncating, throwing away everything. Don't do anything else. So if you want to design other types of filters, all you need is their expression for the impulse response. So other types of filters that you encounter, for example, you can have an FIR bandpass filter. In which case we have two frequency values from minus pi to pi. We say it goes from omega C1 to omega C2, and the same on the negative side. Once you write down the Fourier transform of your bandpass filter, which is 0 from for absolute value of omega less than omega C1, 1 for omega between omega C1 and omega C2, and 0 for omega C2 is less than omega less than or equal to pi. Once you do that, you can simply compute its impulse response, bandpass, and that comes out to be sine of omega C2n over pi n minus sine of omega C1n over pi n for n from minus infinity to infinity. So if you now want to get an FIR filter from this, again, you simply shift it by m equal to n minus 1 divided by 2. You keep everything from 0 to n minus 1, throw away everything else, and you have an FIR filter. You can similarly ask, what is an FIR bandpass filter? Again, I'm not writing the expressions for HN because they are as simple as just doing the shifting and saying everything gets truncated. So FIR bandpass, the main question is what is the frequency response? Your bandpass filter band stop filter and that is you just have one band where it is 0 and everywhere else it is non-zero. So it still has omega C1 and omega C2, but now it is going to block frequencies between these two ranges. So your desired frequency response is absolute value of omega less than or equal to omega C1, 0 omega C1 is less than absolute value of omega and omega C2, and then 1 for the other ranges. Okay. And if you compute the inverse Fourier transform of this, you get HDN equal to 1 minus omega C2 minus omega C1 over pi for n equal to 0, and you get sine of omega C1n over pi n minus sine of omega C2n over pi n for n not equal to 0. So you just take this impulse response, shift it by m, truncate it, and you get your FIR filter, which will be very close to whatever the filter you desired. Another filter that you might be interested in is what's called a multiband or a multilevel filter. This type of a filter is what you would use if, for example, you were designing a digital equalizer. You have different bands that you want to either shift up or shift down. So a multi-level filter, and I'm going to only draw the positive frequencies. Basically, you chop off the 0 to pi region into, let's say, k region, into L minus 1 region. Then you say the first region I want this response, then the next region I want this response, the next region I want this response, and so forth. So what you do is you just put down these different edges of this desired frequency response. So you call this point omega 0, which is 0. Omega 0 is always equal to 0. You call this point omega L, which is always equal to pi, and then this is omega 1, this is omega 2, and so forth. And whatever height you want in the band between omega 0 and omega 1, you call this, for example, A1, you call this A2, and so forth. So mathematically, a multi-level filter has a frequency response which looks like the following. It is equal to AK for omega k minus 1 is less than or equal to omega is less than or equal to omega k. And your k goes from 1 up to L, and the assumption is that omega 0 equal to 0 and omega L equal to pi. So if this is the filter that you are interested in, then if you take its inverse Fourier transform, you get HDN, which is simply equal to L from 1 to capital L, AL minus AL minus 1, AL plus 1, sine of omega L n over pi n, for n from minus infinity to infinity. So if you were interested in, for example, designing an equalizer where the first band of the equalizer goes up to, let's say, some 200 hertz, the next band goes from 200 hertz to, let's say, 1000 hertz, and so forth, you just figure out the corresponding discrete frequencies. And then if someone says, I want the gain in that equalization range to be, let's say, 20 dB or minus 20 dB, that just determines your AK values. And so you get this expression, and if you want to now design an FIR equalizer, because this equalizer you can't implement, an FIR equalizer, you simply shift all of this by amount m, and then just cut off everything from 0 to 2m, outside 0 to 2m. Okay, so designing an equalizer or a multi-level filter is as simple as just taking this formula, shifting it to the right, and cutting it off after the desired range. Yeah. This, if I had a low-pass filter is just a multi-level filter with A1 equal to 1 and A2 equal to 0. And you only have two levels. So if I just plug it in this formula for H low pass, I get exactly my formula, what is sine of omega Cn over pi n. So this single formula actually is the generalization of all the other band stop, band pass, high pass, and so forth. So if you can just remember this formula, you pretty much know any type of filter which looks like a piecewise constant in the frequency domain. Your textbook talks about the impulse responses of two other types of filters. One is the 90-degree phase shift filter, which is commonly used in communication systems for what's known as the I channel and the Q channel. And then there is a differentiator filter. Again, I'm not interested in writing those down here because if you just write down the impulse response of the ideal filter, getting an FIR filter from that is trivial using the window method. Okay. So the basic principle of window method for FIR filter is very simple. The question that we have not answered so far is the following. What is the effect of windowing on the desired frequency response? And effectively, the two questions are connected to each other. What should be the length of my FIR filter? Because what we can be sure is that we have started with a filter which has infinite duration, and that infinite duration filter is what basically implements the ideal frequency response. But now if my filter is no longer infinite duration, I can't expect it to give me back the frequency response that I started with. What did I end up with? What is the new frequency response that I have? And that is connected to what should be the length of my FIR filter. Does increasing the length of my FIR filter or decreasing the length of my FIR filter make it appear closer to my desired frequency response? So those are the questions that we want to address, and for that we'll look at the windowing operation in the mathematically and try to understand its effect in the frequency domain. So remember, the way we are getting Hn is equal to, we take our desired impulse response and we multiply it with a window Wn. So what is the frequency response of this Hn? Our mathematical operation is, we are throwing away the values, but our mathematical operation is, we are starting with one impulse response and a window, and we multiply the two. What happens in the frequency domain? We'll have in the frequency domain periodic convolution, because our Fourier transforms, discrete time Fourier transforms, are periodic, so we can't have the canonical convolution. What we'll have is periodic convolution, which is given by, so the difference between a regular convolution and periodic convolution is that you only do the integration over one period rather than from minus infinity to infinity in regular convolution. So you will have minus pi to pi. Whatever is the Fourier transform of this and whatever is the Fourier transform of this. So let's first figure out what are the Fourier transforms. So Hd of n minus m has a Fourier transform Hd of e to the j omega, which is the desired frequency response. And what effect does the time shifting have? It will create simply a phase shift, e to the minus j omega m. So the Fourier transform of this shifted impulse response, of course, looks still like the Fourier transform that we want. It's just shifted version. What is the Fourier transform of Wn? Right now I'll just call it as phi r e to the j omega, and we'll explain that later. Okay. So what it looks like is I get Hd of e to the j omega, e to the j theta, e to the minus j theta m, times phi r of e to the j omega minus theta d theta. Okay. So this is just my convolution formula. I have just written it as x of t, h of t minus tau, but now the variables are omega and theta rather than t and tau. Now I want to get rid of this. I want to get rid of these linear phases just to simplify the calculations, because the linear phases are not giving us any information. All these phases are linear. They are just created by a linear shift. So these linear phases are not going to create any difficulty. I'm going to just focus on the case without the phases. So I want to evaluate 1 over 2 pi minus pi to pi hd of e to the j theta and psi r of e to the j omega minus theta d theta. Okay. This is my desired impulse response. I am multiplying that with a flipped version of my rectangular Windows Fourier transform, and then I'm shifting it. Then I integrated the usual convolution formula, and then I divide it by 1 over 2 pi, and we have to understand what effect that is having. So let's first verify what is the Fourier transform of my rectangular window. So the Fourier transform of Wn is given by sine of n omega by 2 divided by sine of omega by 2. And of course, since we have the shifting of the window, our window starts from 0, we have this phase shift. But the Fourier transform of Wn between minus pi and pi looks very much like a sinc function. It is not sinc because it is periodic. It's sine over sine. It has a sine over sine form. Okay. So what is happening is that, let's take the example of low pass filter. My hd of e to the j omega is given by this form. It has a cutoff from minus omega c to omega c, minus pi to pi. This is the desired frequency response. But when we do the windowing operation, instead of getting this frequency response, what we get is we get its periodic convolution with this hd of e to the j omega gets periodically convolved with this Fourier transform of my window function, which looks like the following. It has this form, but only up to pi, and after that it repeats itself. Okay. So instead of getting this thing, I am getting convolution of this and this, and you can be sure that when I convolve this, the end frequency response that I get won't be this ideal low pass filter. So what will be happening to my the frequency response? What happens to h of e to the j omega is that the edges of the filter get a smooth, and the smoothing effect happens because you are doing this convolution with this sinc-like function which has a huge bump with a non-negligible width. Okay. And also what happens is that you get ripples in your final frequency response in h e to the j omega. So here is a pictorial depiction of what happens when you take your desired frequency response and convolve it with the Fourier transform of your window function. For each value of little omega, so if you want to evaluate at little omega, here we are fixing our desired frequency response, that is fixed. And then you flip your this sync-like function, of course it's symmetric, so flipping doesn't do anything, and then you slide it across for different values of little omega. Now when you slide it, and then you integrate the expressions, what happens is that instead of getting this smooth edge that you wanted, because of this thickness in your frequency response of your window, you get actually some time, you get some non-negligible width for your frequency response to go from 1 to 0. Okay, so that is one of the effects that happen. The other effects that happen is that instead of this getting plain line of 1 or 0, what you get are these ripples in the frequency response because of this oscillatory shape of your frequency response of the window. The only way you can make it ideal is if your window was really very narrow, which means it approximates an impulse function, an impulse delta, as closely as possible. But the only time that will happen is if your length of your filter was very large. Okay. So if you look at this is your new impulse response that you get. This is your frequency response after the convolution. And the two types of effects that you see, one is this non-negligible transition from high to low, and the other ripples, they are both caused by different aspects of your window's Fourier transform. So this is the Fourier transform of your window, and this is what is called the main lobe of W of e to the j omega. So the main lobe of your window's Fourier transform, and these are called the side lobes. Okay. And the effects of rippling in your frequency domain are caused by the heights of your side lobes and the transition of your frequency response from 1 to 0 or 0 to 1 is caused by the width of your main lobe. So we have done a little hand-wavy argument about what happens to your ideal frequency response. Now let's try to understand what are the things that explicitly affect your frequency response. So for that, we'll look at the nature of the frequency response of your window. So for a length n window, length n filter means we have length n window, which we'll write it as 2m plus 1. And its Fourier transform is given by W e to the j omega equal to sine of n omega by 2 over omega by 2, sine of omega by 2, absolute value. If you plot this Fourier transform what you get is a picture like this, from minus pi to pi. The height of this thing is 2m plus 1. You can obtain that from the L'Hopital's rule, or capital N, which is capital N. The width of this, where it hits the two zeros, so this endpoint is 2 pi over n, and this endpoint is minus 2 pi over n. So this width is, which is called often the main lobe width. Main lobe width is equal to 4 pi over n, or 4 pi over 2m plus 1. Okay. Now, in most cases, what happens is that there is one side lobe which is the highest. So this side lobe, the highest side lobe in the rectangular window, the first side lobe is the highest. This is called the peak side lobe. Peak side lobe. Okay. And there are different effects of the main lobe width and the peak side lobe height. Okay. So let's try to understand that. So your ideal filter, so what effects do windowing have? As we talked about, there are two main effects. Let's look at those two effects step by step, and let's try to argue what shape of the window function Fourier transform affect which parts of my frequency response. So the first effect we said was we have smoothing of the transition band. So what happens is our ideal filter, we always have, and it doesn't matter if we have low pass or high pass or band pass, we always have a transition from some value to other value. Our ideal filters have a transition like this, for example. This is my HD e to the j omega. I am not plotting the whole frequency response. I'm just giving you what is happening. If, for example, if this was omega c, what happens in reality is that you get actually a frequency response which goes like this. There is a smooth transition from 0 to 1. And this transition, if you think about it, if I say this is my width of my transition, this width of the transition is proportional to width of the main lobe. Okay. So if we want the transition to be sharp, let's focus only on the case of the window that I have shown you. If we want the transition in the frequency response to be sharp, if I want to make a low pass filter which goes very quickly from 1 to 0, my transition width should be small. And if I want the transition width to be small, what should happen to my main lobe width of the window? I want the main lobe width to be small if I want the transition to be sharp. Now, so the goal is sharper transition implies smaller main lobe width. It's important for you to understand we are talking about the main lobe width, not the height of the main lobe. Okay? The height of the main lobe grows with increasing value of m. But the main lobe width is inversely proportional to the length of my filter. So if I want to make my main lobe width smaller, what do I have to do to the filter? So since my main lobe width formula is this, which is 4 pi over n, it's inversely proportional to the length of my filter. So sharper transition, smaller main lobe width, which means larger FIR filter. Okay. That's the first aspect that we need to be familiar with. Depending upon what is our required transition width, we are going to determine the length of our filter based upon this main lobe width formula. Now, the other effect that windowing creates is it creates ripples in both what I call pass band and stop band. So again, what we want is an ideal response like this. What we get is, and I'll just extend that a little bit to create the idea. So this is my ideal h of e to the j omega. But what we get are these oscillatory effects like this. Then there is this non-negligible transition. And then I have oscillatory effects again. Okay. So instead of staying at 1, for example, I actually get a response which goes up and down around 1 and a response which goes up and down around 0. It's never perfect 0. Okay. So these heights, they are represented in the linear scale as delta, these ripples, or the maximum size of the ripple. And the question is, what is that delta a function of? So this delta is a function of the ratio of the peak side lobe height to the main lobe height. So it's a ratio of peak side lobe height divided by the main side lobe height. And this number is often represented, this part is often represented in the dB scale as, so it's called a side lobe in dB, that is equal to 20 log 10 of peak side lobe divided by main lobe height. Now, if we want to decrease the transition in going from 1 to 0, the idea is we can make our filter length larger and it will make the transition width smaller. But for the ripples, what happens is that no matter what, it's part of what you would have seen for earlier. It's called the Gibbs phenomenon, which is that regardless of the length of the filter, ASL or equivalently delta stays the same for rectangular window. For rectangular window, this ASL is 13.3 dB, and this delta in the dB scale is about 21 dB. Okay. So regardless of what is the length of your filter, the attenuation from the pass band to stop band for rectangular window stays at 21 dB. You are stuck there. You can't have more attenuation than 21 dBs. When you are dealing with rectangular window, you can make the length of the filter 1,000, 2,000. The only time it will go to zero is if you make it infinite length, which we can't do. But the transition width of the filter is a function of the length of your filter. So transition width is proportional to 4 pi over n. So we'll just verify that using the MATLAB tool again. So we'll try to do this now for high pass filter, because all the discussion that we had, it's not just specific to low pass filter. It applies to any filter that has a stop band and a pass band. So this is the case where we designed a length 10 filter using rectangular window. My cutoff was 0.6. Okay. And you see that around 0.6, it is starting to drop, but pretty much if you go from this point, which is 0.7 to 0.5, it takes it about like 0.2 pi to go from pass band to stop band. And let's look at the height of this maximum height that you have. That is about minus 20 dB. So we have, if you zoom in, you'll get minus 20 point something or minus 21 dB. Now let's increase the length of the window, which means increase the length of the filter. I make it double. So what I expect is, from the formula of transition width, if I double the length of my window or my filter, the transition width should become half. It's inversely proportional to the length of my filter. But what I would also see is that this top attenuation factor won't go any lower. It will still stay at minus 21 dB. So let's look at it. Pay attention to this side lobe height. The other side lobes will go down. That is not the point. The point is the one immediately next to my pass band won't go down. And also pay attention to the amount it takes it to drop. So you see that now I effectively, this transition width has significantly, it had previously going up to 0.5 to come here, and it was starting at 0.7. Now I'm about starting at like 0.65 and 0.55. So the transition width has halved. But if you look at this attenuation factor, it is still sitting at minus 21 dB. Okay? Which is related to the fact that for rectangular window, as I keep on increasing the length, the main lobe width is decreasing, so my transition width is decreasing. But the ratio of my peak side lobe height to main side lobe height stays the same, so my ripples don't decrease. So let me just now double it again to 40. Now the transition width should even half from this point. But again, if you look at this top point, this attenuation factor, it will stay at minus 21 dB. So as you can see now, the transition width significantly reduced. Okay? But this top point is still sitting at minus 21 dB. The rest is going down, surely, but this first side lobe doesn't go down. And the same height stays true if I were to do it using a low pass filter. If I just do a low pass filter with 0.3 and I say design, you see the filter is of course just now a low pass filter, but this first side lobe is still sitting at minus 21 dB. That distance stays the same. It is always minus 21 dB relative to your pass band. Okay. I could of course have made my pass band be 21 dB and the difference will still be 21 dBs. Okay. So it's the dB scale, it's not an absolute value. If I reduce the length of this filter from 40 to 10, so I have reduced it by a factor of 4, my cutoff, which is at 0.3, the transition width should increase by a factor of 4. Although this point will stay minus 21 dB. I do that and you see that it's around the same minus 21 dB, but now my cutoff has really increased. It's now 0.2 to 0.4. Okay. So in filter design, if I fix my window, no matter what is the length of my window, my attenuation in the stop band is not going to decrease. And that's due to the Gibbs phenomenon. But my transition width will decrease. Okay.